All right, so let's get started without much delay. I'm excited to welcome Henny Admoni today for the colloquium. Henny is a postdoc at CMU. She recently finished her PhD at Yale University. We're actually going to hear both from her PhD advisor and her postdoc advisor later in this quarter. But as you know, the students and postdocs do all the work, so we get to hear from the real person who did the work. She's been doing some great work on assistive robotics in different contexts. So I'm very excited to hear what she has today.
Awesome. Thanks. Guys, thank you. So thank you, Maya, very much for that introduction. I am happy to be the opening act to my two advisors in the coming days, my PhD advisor, Skaz, and my postdoc advisor, Sid. But I'll tell you all about the research that I did. So I'm going to be talking today about how we can recognize human intent when we look at human-robot interactions. And the particular domain that I'll talk about is assistive robotics. So first, to give you a little bit of background about me, as Maya said, I am now a postdoctoral fellow at Carnegie Mellon at the Robotics Institute there. I've been there for 4 months, and before that, I did my PhD with Brian Scazzolati at Yale University. I worked in the social robotics lab, and my PhD research was on nonverbal communication for socially assistive robots. So I work with robots that help people. And there are lots of ways that robots can help people. I probably don't have to convince most of you that that's true. Robots can act as assistants in the home. They can help people to manipulate their environments. They can act as teachers and tutors for children. They can act as coaches or motivators. And there's actually there are plenty of other areas where robots can assist people in personalized one-on-one interactions. And all of these interactions fall under the guise of human-robot interaction, and that's my field. I look at how people and robots can collaborate, and how we can make robots that are easier for people to use and that help people in their daily lives. So generally, we divide this in the field into 2 areas, and the first is socially assistive robotics. These are robots that interact with people through conversation, through the environment necessarily around people. On the other hand, we have physically assistive robots. And these are robots that are making some impact, that are having some effect in the physical world to help people. So these range from assistive robots that I'll talk about later that help people with mobility impairments to interact with their environment, all the way to robots that help you clean up your table after dinner or vacuum your floor. So as I said, in the field we have this concept that social assistance and physical assistance are very different things. And there are different challenges to robots that have to have conversations with you versus robots that have to pick up glasses. But at the same time, there's actually a lot of underlying content that is universal across all human-robot interactions. And that's what my research focuses on. And in particular, I look at intent and how we can measure human intent and how we can produce robot intent to improve these kinds of socially and physically assistive interactions. So I'm going to be coming back to this figure a lot during the talk because it sort of gives a high-level encapsulation of my work. I look at both how we can recognize human intentionality from human behavior and how robots can express intent to people so that they are better communicative agents, so that they are easier for people to understand. So I'm going to start with the recognizing human intent, because the first question you should ask is, can we even do that? Is it even possible to recognize human intent? And this is actually kind of a challenging problem. And the reason it's a challenging problem is the following. So here we have a person and a robot, and there are objects on the table, and the person is trying to communicate to the robot what object they would like to pick up. And the person may have some concept in their mind of their intent, right? This person intends to reach for the telephone. They can't reach the telephone, so they'd like the robot to get it for them. But the robot has no idea what is in the person's mind. minds are not observable. And so the only thing the robot can use is the human behavior. And it needs to draw on human behavior in order to recognize intent. But there's not a one-to-one mapping of behavior to intent. If the individual reaches their hand forward, they could be reaching for either the vase or the phone. And so going from this behavior to intentionality, to recognizing intentions, is the challenge of human-robot interaction, the challenge of my work. So I'll talk about a first project that I did that just basically shows that we can even detect and recognize human intent from human behavior. And in particular, my work looks at nonverbal communication. So I'm asking an even harder question. Not can we recognize human intent from the full range of human behavior, which includes all kinds of vocal and non-vocal effects. My research actually focuses on very specific nonverbal communication, which is eye gaze and gesture. And I chose these two specific portions of nonverbal communication because they are easy to measure and they're predominant across all of the literature in collaboration and nonverbal communication. So all of my work is going to be talking about how people use their eyes and how people use their gestures to communicate with each other. So let me give you an example. I'm going to show you a video. And in this video, the woman facing the camera is a teacher. She's teaching her student how to play a board game called Transamerica. It's a spatial board game, so she's going to be making references to this map. She'll be using a lot of nonverbal behavior. So I want you to look especially at her eye gaze and her gestures as she tries to communicate this information.
Are you fine with being like the green player?
Yeah, green works.
Okay, I'm yellow.
Okay.
So basically, like, these two things, they kind of keep track of your progress across the entire game.
Oh.
Okay, so that was a very brief clip, but from it you can probably see the rich complexity of nonverbal behavior that we have to work with. We can divide the kinds of communication that you saw in the video into different kinds of intent. So she was not, during the entire statement, constantly giving information about the game. There was actually a lot of communicative behavior that's not about conveying facts. For example, you can convey spatial references, which is when you're asking someone to look spatially or to observe spatially something in your environment. You can be performing a demonstration, and I saw this a lot with spatial games. Demonstrations were not something that people who looked at nonverbal behavior for conversation had considered, because those gestures, like the gestures I'm making now, tend to be a lot more abstract. But when you're actually teaching something physical, you do a lot of demonstrations. There are also behaviors that people do because we need to think. So floor maintenance behaviors are the ums and the ahs that people use to maintain the speaking turn, the speaking floor, while taking a pause. And then there are interactive behaviors, so question and answer behaviors that are seeking some sort of response from a partner. And these, I found, fell into a different category. So let me give you an example of the different kinds of nonverbal behaviors that people use in different communicative contexts.
Kind of keep track of your progress across the entire game.
So it's a short clip, but she was giving a fact about the game, and she was making a gesture that was referencing the table, and she was making eye contact with her partner. On the bottom, I'll show you a video of a floor maintenance behavior. It's really short.
So basically, like,
if we want, I can play that again, because I know it's like hard to see.
So basically, like,
and the nonverbal behavior that happens during floor maintenance is different than the nonverbal behavior that happens during fact communication, often. And the reason these are important is because we want to know what communicative context we're in so that the robots and our systems can know whether the information being conveyed is important. You don't need to perform expensive natural language processing on the floor maintenance behaviors. You don't need to put that in a database for later, but you do for the facts. And for facts, you want to parse out different information than you do for spatial references. So being able to identify these contexts automatically is actually really useful. Yeah?
Maybe I missed this, but is there evidence that people interact with robots with the same nonverbal cues that they do with other people?
That's a great question. And that's kind of an assumption that underlies a lot of our work, is that people will treat robots the same as they treat other people. There's a lot of debate in the field, let's say, about what it takes for robots to be treated as animate agents. The next study I'll show you shows a way of getting a robot to appear animate by having it do something unexpected. But the prevailing thought is that, yes, if robots can appear sufficiently intelligent, then people will behave with them the way they behave with other people. But there's definitely a lot of room for investigation in that. So we have all of this nonverbal communication, and we can extract all kinds of features out of it. We can look at the eye gaze that the speaker is using. We can look at her gestures, her arm motions, and we can look specifically at her deixis, her pointing behaviors, both with her fingers and with her eyes, or other parts of her body that reference particular spatial locations. So what I did in this project is I went through the literature and I identified specific categories of each of these features. So values for eye gaze and gesture and deictic references that were well established by psychology literature. Some of these came straight out of the psychology literature. So iconic, metaphoric, deictic, and beat gestures are very well established across all the literature in nonverbal gesturing. But what I found, as I mentioned, is that all of this work had been on conversation and didn't account for demonstrations or functional gestures, like shuffling the cards when you're teaching a board game. So oftentimes you'll be shuffling the cards while you're giving a piece of information or doing a floor maintenance behavior. So I added those to this schema. And so you can take, I recorded people teaching each other, so human-human interactions. And I discretized the videos, chopped them up into half-second blocks, and each of those blocks was an observation. And each observation is just a feature vector of the gaze, the gestures, and the deixis for the teacher, and then also the gaze and gesture for the student. We found the students didn't perform a lot of deixis in this interaction. And each one of these vectors was labeled with a context. And this was hand-coded. So someone had to go through and listening to the speech and looking at the dialogue, say what the context was. So what I'd like to do here is to take these observation features and be able to train a model so that when I get a new observation, I can predict the context of that observation. So given a new set of nonverbal behaviors, what is the context that I'm in right now? And you can actually do this. I did this in a very rudimentary way. You can certainly be more sophisticated about it. But even with k-nearest neighbors, where you're just looking for similar examples, you can identify context. So simple k-nearest neighbors algorithm, you have your set of observations that you've already seen. You have some number k for neighbors. I found in this case that 2 was actually sufficient. And a new observation of behavior. And then you find a set of neighboring observations based on this information, and you assign the new context based on the majority of the observations. Pretty straightforward. But even with this algorithm, this simple algorithm, we performed significantly better than chance on this task, and even better than a sort of naive algorithm. So what you see in the graph is the accuracy of prediction on a new of classification of a new observation. The dotted line at 11% is chance, and we performed at about 46% in using the model. The most common classification was a naive method, so rules were basically the most dominant form of communication. So if you always stuck with rules, you would do about 37%. So that's what you see here. Yeah.
Are these features computed over a certain time period, or how much do they capture of the temporal evolution of the...
That's a great question. Mm-hmm. So the features were computed for every half-second chunk of video, and I actually took into account both the past one time step and the current time step to try to account for the dynamics of kind of the changing interaction. But you could have a much more sophisticated model that accounts for the temporal dynamics of that, for sure. And this is a video, so it's the same video you just saw, but in the upper right-hand corner, there are 2 lines. The first is annotation, is the human ground truth, what our coder said was actually the context of the interaction. And the second line is prediction, so what the system automatically predicted that observation was. You can see.
So then, are you fine with being like the green there?
Yeah,
Is
green
it
works.
Okay,
I like
I'm
it.
yellow.
Okay.
So basically, like these 2 things, they kind of keep track of your progress across the entire game.
Okay.
So it's not perfect. But when you consider the fact that you are trying to predict context simply from nonverbal behavior and not at all from any of the natural language that's being generated, you think it does pretty okay. Adding natural language into that would obviously make the classifier way better. So this is just a sort of initial idea that we can even recognize human intent from nonverbal communication. The next question is, does it matter, right? Can robots even convey nonverbal behavior to people? So is all the effort in getting robots to produce nonverbal behavior even worthwhile? Can people recognize nonverbal behavior from robots? And that's this is the second study. So this is a study I did actually at CMU as an intern. So for all the PhD students out there, some PhD advice is spend a month or something like that in a different lab. Go see other parts of the academic world. It's really helpful to kind of broaden your network. So we wanted to see if people could understand robot intent and do counterintuitive actions based on what a robot asked them to do. So this is a robot called Herb. It's a bimanual manipulator at Carnegie Mellon. And in this experiment, Herb was trying to get people to sort blocks in an unusual way. So people sat down in front of Herb, and we were evaluating, so people sat down in front of Herb. Herb would hand people a block, a colored block, either yellow or blue, and you can see there's a yellow bin and a blue bin in front of them. And what we were looking at is, could Herb convince people to sort the blocks into the wrong bins, essentially? So we told people that, Herb looks at them, hands them the block. There's a force torque sensor in the wrist, so whenever anyone took the block out, the hand would release it. We told the user they could sort the block wherever they wanted, but if you saw just there, Herb turned his head in one of the 2 directions of one of the 2 bins. So we told people, you can sort the blocks however you want, Herb will provide a suggestion. Go. And didn't give them any more information than that. They did 5 trials, and they got a couple of different kinds of blocks on these trials. So the easy conditions, let's say, are solid blue and solid yellow. So what we found is that people almost always sorted the blocks into the corresponding color bins, right? Blue blocks go in blue bins. That's sort of the way we're trained. Some of the trials had ambiguous blocks, and these are blocks where half of the color is blue and half of the color is yellow. And these don't have a majority color, so you could say they could be sorted in either direction. What we found with these is that people often sorted them by the top color. So the color that was on top when the robot gave it to them was the color they sorted it by. And then you have semi-ambiguous blocks, which have a majority color and have a top color, but are not as obviously sorted into one of the 2 color bins as the blue blocks. And so our goal was, when Herb handed people an ambiguous or a semi-ambiguous block, it would always turn its head to the counterintuitive bin to sort. So if you got an ambiguous block that looked like that with blue on top, Herb would turn its head to the yellow bin. And we wanted to see if people would follow this kind of suggestion from Herb. So to give you a sense of how the experiment progressed, this is a timeline with 0 seconds at the point where someone takes the block from Herb's hand. So Herb looks at the target, right? This is over the shoulder view from the robot. Looks at the user sitting across from him. There is force sensed on the force torque sensor, and Herb can release the block. And then Herb, turns right after it releases the block. It turns to look at one of the 2 bins, as I told you before. So in the no delay condition, this is the control condition. Herb opened his hand as soon as a handover happened. And I should say, actually, that I meant to say earlier, this is research that came out of handover literature in human-robot interaction, including stuff that Maya has done on how to perform seamless handovers. So everything that we had done to this point was all about how do you make handovers as smooth as possible, with no glitches and with no problems, because we want people to be passing objects back and forth with robots naturally. We added a kink in the system, though. So the control condition was a no delay, was a smooth handover. The experimental condition had a delay. So for 1 second, instead of letting go as soon as the person put their hand on the block, Herb held onto the block for 1 second while it turned his head. And this is the only manipulation we did between participants. So people either saw the delay condition or the no delay condition. Everything else we kept exactly the same. But the way they treated the robot from that unexpected behavior changed completely based on what condition they were in. So I'll show you a video. The first 3 participants here are in the no delay condition, and the second 3 are in the delay condition. So in the no delay, in the control, you can see Herb handing blocks. Herb looks at the suggestion. The user totally ignores him. They don't even look at the robot's face. They don't care about the robot. The robot is a tool for producing blocks here. And they were really bored. In contrast, when there was a delay,
half and half. What do you want me to do? Okay, I got it. Okay, it's right here. Make the blue side up. Make it look like blue. Okay.
we'll put it blue side up. We'll make it look like blue, he says. Because he knows the suggestion is counterintuitive, but the robot wanted him to put the block there. It's clearly a very hard choice. All right, so what is going on here, right? Something about this handover delay is causing people to all of a sudden see the robot as an agentic being. And that kind of goes back to your question of, will people treat the robot like it's intelligent? My answer is, if it does something intelligent or surprising. So these are just numbers to show you what you already saw anecdotally in the video. We have the rate of compliance, so how often people sorted the block counterintuitively based on what condition they were in. So for the ambiguous block, where it was very easy to think that the block could be sorted one way or the other, we saw a significant difference. But more importantly, in the semi-ambiguous case, where there were a lot of reasons for people not to follow Herb's suggestion, we saw a significant difference between the conditions as well. We also saw other statistics, like that people spent more time looking at Herb's face when the handover was delayed. And people recognized that Herb had made a suggestion. So when we asked them after the fact, they reported that Herb had made a suggestion significantly more often when there was a delay. So we're using these nonverbal behaviors to express intent that comes from a completely different modality. So Herb is basically using gesture to tell people to pay attention to its gaze. So there's an interesting multimodal communication problem there. Okay, so we've shown that we can both recognize human intent and express robot intent. But how do we even go about performing this? How do we develop robots that can show people that their intents can reveal their intents to people? Let's say. And so that's the project I did most recently at the end of my PhD. Was looking at how robots can communicate spatial information to people during a human-robot collaboration. So the premise here is fairly simple. You have a robot that is a collaborator. This is a socially assistive robot because it's not actually physically helping you pick up the pieces and put them together, though there's plenty of great research that does that. This is a robot that acts as a tutor, basically, that gives you instructions on how to put together this IKEA chair. And the robot wants to be able to communicate verbally things about the world, like saying the large wood block. But there's also nonverbal behaviors that can support these kinds of verbal expressions. So for instance, if the robot wanted to talk about the small wooden blocks in front of it, we've got two small wooden blocks, and they look the same when they're very close together. Saying the small wood block might be an insufficient verbal reference. So how can you use nonverbal behavior to help disambiguate that? That's kind of the motivation. The intuition behind this research is that different nonverbal behaviors have different costs. So a look might be less costly than a point. And this is for a lot of reasons. You can think of it purely from a mechanical perspective. It uses less motor energy, less motor power to turn the robot's head than it does to move the 3 degrees of freedom or whatever, to turn the robot's arm. But you can also look at it from a cognitive load perspective, that small motions and eye gaze are things that we recognize kind of intuitively and very subtly. A robot that points to every single thing that it's talking about might become visually distracting, and you might actually lose the importance of that gesture. And so we have this kind of heuristic, this idea that there's a lower cost for gaze than there is for pointing, and there's a lower cost for pointing than there is for both gaze and pointing simultaneously. So to build these behaviors, I built a model that takes in information about the scene, about the environment, and outputs the behavior, the nonverbal and verbal behaviors that the robot should do. In this case, the verbal behavior was always present. The robot should always make the verbal reference, just what nonverbal behavior should it support with. The model has a set of inputs, so I'll go through the inputs. All of the objects in the scene become an input to the model. So what is available in front of the robot? What's the target object in this case? Tau. The set of behaviors the robot can actually perform. So in this particular case, it was looking, pointing, or both. But that doesn't mean that that is the case for all robots. And so this model is robot agnostic in the sense that you can plug in whatever behaviors you'd like. The cost, the relative costs that I talked about for the different behaviors, and some threshold alpha that represents how clear you want your target object reference to be over other potential object references. So the way this model works is it calculates a score for each of the objects in the scene. We calculate a score that we call the referential likelihood score. And we take into account both low-level and high-level visual features of the scene in order to produce this score. So again, going back to what we know about psychology and how people process visual scenes and how people incorporate that information into their attention models. So for each object, we have a score sigma for that object I under a particular nonverbal behavior J. The score is just a linear sum of low-level features like the saliency. So if you've ever seen the classic visual saliency research that people have done, IDI and Koch and things like that, we took that visual saliency algorithm, looked at the scene. Verbal references, so these are high-level features of the scene, so information about the context that is used to direct attention. And then the nonverbal behaviors that people perform, so the eye gaze and the pointing that's going on. And we model for each possible nonverbal behavior what the likelihood reference score would be for each of the objects in the scene. So here we have the likelihood reference scores for these objects in the scene. Once we have that, we look at which behavior maximizes the referential likelihood score for the target object while minimizing the overall cost. So we basically start at the least costly behavior, and we say, what is the b-value? So what is the referential likelihood score? Is it sufficiently high enough above the standard deviation of all the referential likelihood scores above our alpha that we've established, or not? And if it's not, we go to the next expensive behavior, and so on. So basically minimize the cost while maximizing how clear the referential likelihoods, the reference is. And And we did this, we validated it both on Mechanical Turk using videos and also doing an in-person study. That's not data that I've included just for the sake of time, but I'm happy to talk about it afterward. So we now have this model that can generate spatial behaviors, referential behaviors for robots. But does it work, right? Like, I've made a model, right? I validated it in these kinds of very limited studies. I wanted to see if it works in actual human-robot interaction. So I developed a study that had people putting together these Lego structures. And the robot would give them information, would give them instructions on how to put together the Lego structures, and then they would have to do that. And they would do that either with nonverbal behavior or not from the robot, and we measured their performance. So the hypothesis is that the nonverbal behaviors that are generated by this model would improve people's performance on this task. And we specifically talk about performance in terms of two metrics, the accuracy and the efficiency. So how well did they follow the instructions? Did they actually do what the robot said? And how quickly did they do it? And actually, specifically, the hypothesis is about increasing difficulty. So not just that any task will need nonverbal behaviors, but that as tasks get harder, the nonverbal communication becomes more and more important to the interaction. So here's a video. It's going to show you what now looked like to a participant in this study when it was using nonverbal communication. So I should say people were doing this in real life, right? This is a video, but they came into the lab. They would listen to a set of instructions from the robot. They would be required to memorize those instructions. They're reasonably short, about 40 seconds, and then build the object. So this was in part a memorization task.
Put one of the small red blocks on top of the large line block. Put the small green block next to the red block. Then stack a small blue block on the red block. Put the arrangement in the middle on your right.
Okay, so some gestures, some gaze, some combinations of the two. And a series of instructions, yeah.
Is the on your right speech part also automatically generated? That's a reference verbally?
It could have been. No, it wasn't. So the bin locations were hard-coded, I should say. So the rest of the experiment was totally automatic. So it was each, you can kind of see it behind the block here. Each block had a fiducial marker, so we could isolate the position of the block with a lot of accuracy, so the robot knew where the blocks were and it could point to them or look at them when they moved around. But the bins were in a particular location. So as I said, this experiment is about increasing difficulty. So how does the increasing difficulty of the interaction affect how important nonverbal communication is? So we increase difficulty in two ways. The first way is just by adding more memorization. So some people saw an easy task, which had 6 steps to memorize, like the steps you just heard, put the red block on top of the green block. Some people had a hard memorization, which was 8 steps to memorize. And it's not a coincidence that this kind of straddles the 7 plus minus 9 kind of heuristic about how many pieces of information people can hold at a time. Turns out going from 6 to 8 was hard. It's a pretty small difference, but it was challenging. The other way we manipulated the difficulty was a little bit more nefarious. So the people in the easy condition had an uninterrupted task. They listened to the robot give the instructions, they put the blocks together, and they did that twice. For people in the hard condition, they listened to the robot give the instructions, and then before they could put the blocks together, I interrupted them. I came into the room, and I handed them an iPad with a spatial intelligence test, a mental rotation test, and I said, you have to do this right now. There are 8 questions, and when you're done, you can put the blocks together the way the robot said. People didn't like this. So this is an example of the spatial rotation test. So you're given an image like this, and you have to say which of these other 4 images is a rotation of the original one. So it's not easy. I don't remember anymore which it is, so I don't want to do it on the fly. And they had to do 8 of these. And the idea behind the spatial interruption was to wipe their spatial memory. So to try to get rid of any kind of mental pictorial representation that they had established about how the blocks should be arranged. So just to summarize this study, we have how much load there is on people's memory, so how many steps they had to memorize, as one condition. And then we had whether there was an interruption or not as a second condition. And then we had whether or not the robot showed nonverbal behavior as a third condition. So we have a 2 by 2 by 2. So there are 8 conditions in this study, and we divided people across. What we found is that the gist is nonverbal behaviors are important, right? That's why I'm standing here. Nonverbal behaviors are more important as the task gets harder. And we can do it in both recall accuracy and completion time. We see these effects. So for recall accuracy, this is averaged across all the interruption conditions. This is just so the proportion of correct responses, so how correct people were at putting the blocks together, they got scored for each structure they built based on how accurate it was. So their accuracy as a function of whether they were in the low memorization condition or the high memorization condition. And we can see an interaction effect here, which means that when they were in the low memorization condition, when they only had to remember 6 steps, people performed really well. They were mostly doing above 90% accuracy. The errors were pretty small. But when they had to go to high memorization, you see this steep drop-off in the participants who didn't see any nonverbal behavior. And the drop-off is mitigated, the line is much more shallow, for people who did see nonverbal behavior. And this difference was significant. Same thing for completion time, except in the other way. Which is to say that when the people were completing the structures at a fairly similar rate when they were in the no interruption condition. Sorry, and I should say this is just for the high memory tasks because low memory was too easy, basically, to see this effect. So no interruption, high memory task, they were very similar. But as soon as we added that interruption, people had to think a lot harder after their interruption in order to remember what block structure they were supposed to be building. And that effect is significant. So the intuition here, the result, is that some tasks, some easy tasks, don't need nonverbal behavior. And so you won't actually see the influence of the models that we're building. But for tasks as they get harder, nonverbal behavior becomes more and more important. And in addition, the model that I talked about before generated nonverbal behaviors that did help people on this kind of task. We've talked a lot about recognizing intent and a lot about generating human intent. I lured you all to this talk by saying it was about assistive robotics. And so I want to bring this in the last 20 minutes that we have back to shared autonomy and assistive robotics. So this is work that I'm doing right now in my postdoc. It's all reasonably new, so I'm presenting a little bit of work that other people have done as a way of kind of laying the base for what I intend to do. So in my lab, we look at how you can take an assistive robot arm and add intelligence and autonomy to it to make it a better tool for people with motor disabilities. So this arm is a Canova, we use a Canova Miko. It's a commercial product that is marketed by a company called Canova based in Canada. And it's designed to be mounted onto a powered wheelchair for a user with mobility impairments like spinal cord injury, things like that, who can't necessarily manipulate their environment with their hands. The idea is that they use the Miko to pick objects up, to pour a glass of water, to brush their hair, things like that, to do tasks of daily living. So this is hugely important for people as a way of increasing independence. The difficulty with the Miko is that, and the Jaco. So the difficulty with these robots is that as sold, they're fully teleoperated, right? And the great tragedy here is that the people who need the assistance the most, who actually need robot arms to interact with the world, are the people who have the least mobility and the least capability of teleoperating those robot arms. If you're lucky, you get a joystick. You have enough mobility in your joints, in your arms to use a joystick that can give you kind of 2 degrees of freedom at a time. Probably not twist, maybe. If you are less lucky, you have a sip and puff interface, which is a straw that lives by your mouth, and you suck in or blow out on the straw, and that is your binary input for controlling a robot arm. And as you can imagine, for this 6-degree freedom manipulator, a binary input device is really, really challenging and is basically not used. So people don't really use the Miko with the sip and puff, but there's no reason why they shouldn't. These are the people who need it the most. So what we try to do is add autonomy to the system. to recognize the human intent from the control they're giving it to the robot, and then have the robot act autonomously on those intentions in order to help people complete these tasks. And I've shown this a lot. So for shared autonomy, we are no longer talking about expressing robot intent. At this point, the robot is part of the wheelchair. It is part of the user, and a lot of people do see it as an extension of themselves. So we've moved from expressing robot intent to acting intentionally. The robot is basically acting intentionally on the user's behalf. And this is an important distinction because you don't want a robot that is fully autonomous, that's bringing you glasses of water necessarily. The goal of this work is to have as much teleoperation as possible, but to seamlessly integrate autonomy so that people feel like they're in control, but they don't have to work so hard to make the robot move. So this is, in part, this is work that Shervin Javdani at CMU has done on predicting people's intent by predicting what object in the world people are trying to pick up. So you can imagine you have 3 objects on the table, and let's say the user is trying to pick up the yellow block that's indicated by the arrow. So the person controlling the robot, the teleoperator, has a policy. We can imagine that they are acting optimally based on this policy to control the robot to pick up the yellow block. And the heat map on the table just represents the trajectory that they're going to follow their policy. On the other hand, the robot doesn't know what the user policy is. So this goes back to the original problem I talked about at the beginning of the talk. They have to predict what the user's intent is going to be purely from the signal the user is giving them. So we model this as a POMDP, a partially observable Markov decision process, where the user's intent is the hidden, is the latent state. And we can solve the POMDP, Shervin solves the POMDP in real time using hindsight optimization. So eventually, as the user gets closer and closer to the goal, the robot narrows down on a particular target and gains accuracy. So to give you a better representation of the system, we have a user using a joystick input in this case. The user's joystick input is the observations to the POMDP. That's what the observations are. The system comes up with an action that the user should perform. So it keeps distributions over all user goals. The states here are the different objects in the environment that the user might want. The system gives a robot action that maximizes the movement towards as many targets as possible. And then the robot acts on the world, and we repeat. So here's a video of our system on the right and the state-of-the-art but more naive single-goal system on the left. The target object is in white, and this will play for each of the 3 objects in the scene. And what you can see is that our system completes the task a lot faster. And primarily this is because by representing this kind of distribution over all goals and being able to act towards all goals simultaneously, the robot can take actions towards the goal earlier. So the action tends to be a lot smoother. You don't get the kind of jumping around of the policy of the prediction as you do with the state-of-the-art.
The input is the pulling on the end effector that we're seeing, the arrows?
So the arrow represents the joystick input. Yeah, so they're using a joystick to control this. Yeah. An interesting observation that we made recently, this is work that I did with Stefania Pellegrinelli, who was a visitor at CMU, is that this kind of shared autonomy system for predicting user goals can work just as well for human-robot collaboration. So there's nothing unique about the system to teleoperation. If we take the POMDP and we flip it around so that it's no longer giving you suggestions of actions towards the user's goal, but it's suggesting an action that is different than the user's goal, then we can also use this for doing collaboration where the robot is fully autonomous and the human is fully autonomous, and they're acting on a simultaneous set of objects, on simultaneous goals. So this is we did a study that evaluated this model that Stefania had developed, this program, based on Shervin's work. So in this study, we have Herb again, And users were brought in and they were told that they have to gift wrap boxes together with Herb. So they all have to act on these 4 boxes, both Herb and the person, but they have different tasks on the boxes. So the user has to use their fine motor skills, which robots do not yet have, to tie bows very nicely on top of the boxes, and the robot has to stamp each box with this marker that he has in his hand. And the way we set it up, it was actually really inconvenient to have the robot stamping at the same time that you're tying the bow. So just very naturally, people avoided operating on the same goal as the robot, rather. So the state of the art in this kind of thing, as I said, is to observe the user's goals, so observe the user's actions, figure out what goal the user wants, and then once you reach a particular confidence threshold on the goal, then you act autonomously. So the robot would watch the user's trajectories towards different boxes. Once it had established that this person is working on this box, the robot can go ahead and work on a different box. The problem with this is that it's not dynamic. You run into these errors where these clashes where the system has predicted the accuracy wrong, predicted the goal wrong, or it has established that the goal is one thing, which was true half a second ago, but the user has changed, and now they've moved to a new goal, and now you have a clash. So I'll show you in these 2 videos. Sorry, that doesn't need sound. You can see this man is tying the bows on the boxes perfectly naturally, but then he switches after the robot has made a determination about which box it should go to, and he has to change his task, right? He's got this little hiccup where the robot's gone to something, so he has to go somewhere else. And you see something similar here, where the user starts to tie the bow. The robot had made the decision to go to that box before it saw her there, and now she has to wait. Right, so not dynamic, really hindering efficiency. On the other hand, when we implemented our model, the beauty of it is that it's constantly updating the user preferences. It's constantly updating this probability on all the goals. And so what you end up seeing is a robot that can dynamically adapt to mistakes that it has made. So here, the woman goes to tie the ribbon. The robot, has initially predicted that it should go to one box, which was a mistake, and so it can seamlessly replan and go to a different box. Yeah, we have time for this. Great. So I wanted to. That's one way of addressing shared autonomy, is predicting the user's goals from the control they're giving the robot, and then acting autonomously to move towards those goals. Another element is addressing the issue of mode switching. So as I said, you have these very low bandwidth input devices, and you need to control a high degree of freedom robot. And so one way of doing this is by switching between modes. So you have a mode for physical translation in space, you have a mode for turning the wrist in 3 degrees of freedom, and you have a mode for opening and closing the finger. And each of these modes are controlled by the same 3 degree of freedom joystick, and you press a button to switch across modes. And this is actually what's done right now for these assistive robots. So this is a video that Laura Herlant at CMU compiled. This is her research. So you can see this is an actual user using the robot arm. They spend a lot of time switching the mode of the robot. This is another user unwrapping a gift. And you can see she doesn't have enough mobility to press buttons. And so to switch a mode, she actually has to remove her hand from the joystick and bring it to a completely different location. So switching modes takes a lot of time, and you do a lot of mode switches when you're trying to do this kind of manipulation task. Laura brought in undergraduates, able-bodied users, to look at how often mode switches happened. She developed this benchmarking framework that's based off of stroke rehabilitation work for real-world tasks. And she was looking at how many mode switches do people perform when they are doing these kinds of real-world tasks, and how hard are they? And the answer is they're really hard. And people are really terrible at them. Because it's really, really hard to keep track of what mode you're in and to switch modes seamlessly. So, the intuition behind the assistance that Laura wants to provide is pretty clever, I think. So let's simplify the three mode space into just two modes. So let's imagine we have two modes, and we can discretize the actions that need to be taken to get to a goal. So we have some target location, right? Some target state that we want to get to, and it doesn't matter what mode you're in when you get to that state. So we can identify that target in both modes, and then you have a way of transitioning between these states, which is just the control that you're providing to the robot. And so the control that transitions, along the plane is moving the robot XY, and the control that transitions across the two modes is a mode switch. And then you can assign values for each of these switches. And then you're just doing graph search. You're trying to figure out the shortest path to get from your start location to your goal state. What Laura observed in her studies is that people behave time optimally. So people will switch into the mode that gets them to that goal state as quickly as possible. And so the way you can assist is by automatically making the time optimal mode switches. So if you are not in a mode that is time optimal to the shortest path to the goal, then the robot automatically switches. And she has a paper at HRI that details a study she did with this that shows that kind of time optimal assistance helps people when they're completing a task with the robot. So a lot of what the lab does right now is looking at taking these kinds of direct inputs. Joystick, we have collaborators who do brain-computer interfaces too. So direct inputs and putting them into this shared autonomy system, and then having the robot act on the world. But my interest is really in the indirect inputs. So what can we learn about all the extra stuff that people do around their direct control of their robot manipulators? So in particular, the eye gaze that they're using. And I'm talking not eye gaze as remote controls, so not kind of the Stephen Hawking's typing out on a screen style, but just the natural eye gaze that emerges when we're interacting with the world and manipulating objects. We can also look at speech in the same way, or biometrics like heart rate or skin conductivity to reveal elements about people's interactions or responses to robot behavior. So I'll give you a quick summary of the talk and then sort of a little bit of high-level vision. So I talked to you about recognizing human intent and how it's possible to do that based on nonverbal behaviors. I showed you a study that proved that people will interpret robot nonverbal behaviors as intentional, and then a model for generating robot nonverbal behavior. And I also talked a little bit about shared autonomy and how it's possible to do both recognizing the intent and acting intentionally in this closed loop when you're doing shared autonomy work, and how important that is. My high-level vision for my overall research is to enable these kinds of assistive robots, whether socially assistive or physically assistive, to perceive and respond to human behavior. And human behavior runs the gamut from nonverbal to verbal behavior. So that's what I'm hoping to do with my research. We have a lot of really interesting collaborations going on right now, not just within academia, but also outside. So for instance, the lab went down to the FDA last week to talk to them about what does it mean to have a medical device that has autonomy, right? How do you even evaluate that in terms of getting it into people's homes and having actual users using this device? How do you classify it? We're working with Canova, and we're talking to them about going this summer to talk to people who actually use the JCO, who've used it for years. So what do we need to know about expert users of the JCO arm? A lot of the studies we do are on able-bodied users or users who've just learned to use this robot platform. Does the shared control need to be different for expert users? And we're pairing with academic hospitals, both the University of Pittsburgh Medical Center Rehab Institute and the Rehab Institute of Chicago, to look at people with disabilities who could benefit from this. So actually bringing our technology out of the lab and into real-world spaces. And with that, I will take any questions. Thank you.
Questions?
Yeah.
So with the shared autonomy work with the joystick and the 3 different objects, it seems like the system can sort of detect the goals pretty effectively after a certain point. Like it knows roughly where to grasp or something like this. Is there a reason why not just have the person select among the 3 goals as opposed to continuously controlling the arm?
So one reason is that we want to maintain that illusion of control. I mean, not illusion, right? It's actually teleoperated control. So if you have a person select one of the 3 goals, then the robot arm is then behaving autonomously after that fact. So you lose the essence of the shared autonomy, which is to keep the user in control as much as possible. Another is that you would have to somehow discretize the space so that you knew what goal the person was going toward. So for example, we don't necessarily need to solve the vision problem that tells us exactly how to grasp an object if we have a user that's teleoperating the robot into the right position to grasp the object. Right? And you do need to solve that with autonomy, with just a selection. So, so we actually get a little bit of benefit of human perception and human intelligence in manipulation.
So was it doing that grasp selection without doing any vision?
So the grasp selection, it was doing vision. It had a couple of, so in this case, it had a couple of pre-generated grasps, grasp points, and it assumed that the person would be happy with any of the grasp points. But for future work, you could imagine you might have some objects you know how to grasp, and there might be some objects in the world you don't. And so for the objects in the world you don't know how to grasp, it's really important that you can teleoperate the robot into the right location for that.
So in some of the parts, there were certain weights for features and costs for certain actions and things like that. Is it easy to find the right balance between those so that you get the desired behavior?
Good question. So finding the balance, I tend to approach it empirically because, right, if you just hand tune everything, then you've overfitted to some system. So for example, for the generating intent work, this one. So for this work on generating nonverbal behavior, there are a couple of weights and a couple, like an alpha. And so the empirical way of finding that balance is showing people different robot actions and measuring how much each of those different features affected their accuracy. So I did this on Mechanical Turk, which is a beautiful tool for getting lots of data very quickly. I showed people videos of robots looking and pointing at different objects. And I measured people's accuracy in identifying the target object. And then I did a linear regression and figured out how important each of the features were to the accuracy. And then basically took the values from that linear regression and plugged them in as the weights. It's a little bit sensitive to domain, right? So if I moved from pointing at objects to maybe doing a completely different kind of interaction, like giving a lecture, looking at a screen or something, I might have to retrain those weights. But actually between the two experiments I presented in that section, so between the generating the model and the real world interaction, I didn't change the weights very much. And they, as you saw, the system worked well enough to produce meaningful nonverbal behaviors in the second part. Yeah.
How do you think some of those nonverbal behaviors may also be able to be used with the assistive robots to communicate with caregivers?
Yeah, absolutely, right. So that's a huge part of communication. Not just communicate with caregivers, but also just be socially effective. So you can imagine if I'm reaching for an object and there's someone standing right next to me, I'm not reaching right in front of their face, right? I'm doing these kinds of grasps. Anka Durgan talks about legibility and predictability of grasps and how important it is to have meaningful motor trajectories for the interaction. So that can absolutely be incorporated into this kind of model, into the shared autonomy work. So you have to have some sense of context, some system that can recognize, for instance, that there are people around, or a system that has training on effective grasps. So something we're looking at is learning from previous examples of motor movements in order to generate these kinds of trajectories. But that's totally an aspect to consider when you're building a system that basically represents a person. Yeah.
Thanks.
for sharing your work with us. In the space of recognizing human intent, with the class of assistive robots which are wearable, say exoskeletons for example, do you think similar principles of nonverbal cues would extend to that space as well?
I think actually that space for exoskeletons and other wearable devices, you can recognize intent in a similar way to the recognizing intent in the shared autonomy work, which is that you have someone producing some kind of motion that the robot is assisting with. I'm assuming this is for exoskeletons that are maybe passive or like that are assistive but not fully taking control. You have some aspect of control of the system, and from the control of the system you can kind of generate the intent. So yeah, we could probably add nonverbal communication on top of that, in the same way that we can add eye gaze into the shared autonomy system to just reveal what people are thinking. People look at where they're walking, and there are studies that show that people turn their heads before they turn their bodies. So we could take advantage of the nonverbal cues there too.
All right, let's thank Henny one more time.
Thanks.